Alright, so let's solve another example, this time involving a cylindrical symmetry. It is question 44. Let's read the question first. Question 44. A long silver rod of radius 3 cm has a charge of minus 5 microcoulomb per centimeter on its surface. Part A, find the electric field at a point 5 cm from the center of the rod, an outside point by the way. Part B, find the electric field at a point 2 cm from the center of the rod, an inside point. So first, let's draw our object. So again, represented in black over here, we have a cylinder. It has a radius of 3 cm. In part A, we want to find the electric field outside the cylinder. So basically, we draw a Gaussian surface, but this time, the radius of our Gaussian cylinder is bigger than the object. All right, so we are given some value also. We are given the object as a radius of 0.03 meter. It's always a good idea to switch in meter. We are given the distance from the center where we want to figure out what the electric field is. We are given the linear charge density. There's a catch with that value. We are given that the linear charge density, lambda, is equal to minus 5 multiplied by 10 to the power minus 6 coulomb per centimeter. We always need to use value in meter. So basically, if there's 5 microcoulomb per centimeter, that means there's 100 times that value in each meter. A meter is longer than a centimeter. So we multiply that value by 100 and we get minus 5 multiplied by 10 power minus 4 coulomb per meter. That's our true linear charge density. Part A, we use the same logic we've been using. We need to find the charge inside our cylinder. Well, in this case, by being given the linear charge density, we're given the charge in the cylinder per unit of length. We simply need to multiply the linear charge density by the length of our Gaussian cylinder to get the charge. The area, this one did not change. It's the area of the contour. It is equal to the circumference multiplied by the length. Notice, again, the length does not matter. They will cancel out. So we end up with this formula. Lambda divided by 2 pi multiplied by the radius, or the point we're considering for our electric field, multiplied by epsilon 0. All right? If we input all the value we have, we get an electric field that is equal to minus 1.8 multiplied by 10 to the power 8 Newton per coulomb. All right? So that's it for part A. This one is really straightforward. Actually, part B is even more straightforward. We are asked, find the electric field inside the rod, but there's a catch in this part. At the beginning of the problem, we are told a long silver rod. Silver. Silver is a conductor. It's a pretty good one at it, actually. So if it's a conductor, that means all the charge inside that object are on the surface. If all the charge are on the surface, that means there's zero charge. There will be zero charge inside our Gaussian cylinder if it is inside the object. If there's zero charge, the net flux is 0. If the net flux is 0, the electric field has to be 0. So that's an indirect proof that if you have the charge on the surface, the electric field inside has to be 0. So really the electric field here is 0. And like I mentioned, it's possible that I try to trick you with a question like this in the test. If it's a conductor, and probably I will mention like copper, silver, gold, let's say, they are all conductor. I think everyone know that. So if you read silver, copper, gold, a metal of some sort, you can assume it's a conductor, no electric field inside. All right. So that's it for question 44. Let's solve one last example related to chapter 3, and we're done with this chapter after this. All right. See you in the next video.